So, now we are going to carry on looking at the data part, basically. Okay. So, this is trying to show you the input part of that. That's roughly speaking how the data part is. Okay. So usually data would come at the input by card. Okay. Whereby it comes into in form of packets with header and data. The header will contain all the routing information and what needs to be done to control the data. Now, once a packet comes at the input port of router, there will be what's called header processing to determine the outbound link and to update the header, maybe to queue it, to buffer it in terms before it gets switched out. Okay, so we would like to look at the components inside this part here, which is the input. Now, the IP lookup, or looking up the IP address, that's one of the major operations that needs to be done by a router on incoming packets, right? So, what happens here, as I said, this basically, this part, it's an algorithm whereby you give it as an input a destination IP address, it gives you the output an outbound interface, basically. Is it clear? Is that clear? It's not clear. Okay. Now, what is not clear about this? It's an algorithm. It's processing block that you give it an IP address as an input, and that IP address is your destination IP address. That part will answer you, would gives you, if you want to go to this place, please follow this. Okay? It's like you asking me now, you tell me I want to go mechanical engineering. I say go there. You tell me I want to go to the head of school office. I say go here. I am the lookup. You are the packet. Okay? So, now this table have in the order of 1 million prefixes, which is the size, typical size of an AP lookup table. Okay? Which means in the order of 1 million entries there. In the order. Now, in order to have that, usually it is called an off-chip DRAM. It's simple to remind. Now, talking about caches and all of that, in this model, you guys have to do some independent study at your own time. It's part of your study to study about the memory technology. What's different between a DRAM, an SRAM, a TCAM, an SSDRAM. You are not required to design one of them, but you are required to understand what is the access time, what is the memory bandwidth, how read and write is performed in this type of memories. This is required. It's your task to do that. Okay? I cannot cover everything. Okay. So, this is an off-chip DRAM. It's dynamic random access memory. Okay? Now, when the data comes in, the lookup would be entering into this address table that has maybe 1 million entry, and you are wishing to get an answer here to tell you, go to interface D, or C, or B, or A. That process is the lookup, and it takes some time. Taking some time is basically looking into a big table, a big array, and searching an entry and getting the answer. That process is, it consumes a bit of time. Okay? After that, what happens? The packet gets header updated, and then it may be queued there also. Okay? It may need to be buffered for a while, and that's called a buffer memory. This buffer memory holds in the order again of 1 million packet. It's again an off-chip DRAM. Usually, it may be something else. Okay. A million packet, if you assume a packet is of 64 bytes or 40 bytes, you can tell me how big is this memory. I'm saying this memory holds in the order of a million packet, and we know roughly speaking what a packet, IP packet size is. You can have a rough idea of how big is that memory requirement. Okay? So these are in the order of couple of gigabytes. Okay? Depending on your router design, there are many things. Answering your question before you asked me about performance. The memory requirement here, there are some rules of thumb in order to maintain good performance of a router in terms of buffer size. Okay? And I give you a small example here. This is not nice. How do I get to explain to you something? You don't see here, do you?
Okay.
Do you? Right here, you can see. You can see. Good. That's the point.
You have to use a blue marker.
Blue. Yes. See. Now imagine I have a computer here. Can you see this?
Yeah.
Very good. I got computer A here. This is a network that has a number of routers. These are routers here. Maybe others, I don't know where here. Sorry. Okay. And I don't know what else. And then there is another computer here, B. And A is talking to B. Okay? Now, in order, maybe this computer here is having an access router. Router R1, and here there is a router next to this computer here also. Router Rn, let's say. Okay? Now we are talking about this buffer memory. That might be here maybe. The rule of thumb says that this buffer memory, the size of it, must be, this memory should hold packets coming from this entity here that is worth of the time of the packets that they go here all the way and get an acknowledgement back, which is TCP. You know how TCP works. That's called the round trip delay on the internet. Okay? So that's the rule of thumb how you size your buffer memory. So this memory must hold around the trip delay worth of packets. So if this link bandwidth here is, let's say, 10 gigabit per second, for the sake of it, okay? And the round trip delay on the internet, if you go on your computer and type ping some address somewhere, you will find the RTT usually is fourth of a second, is 250 milliseconds. It's known. That's the longest round trip delay on the internet, maybe. So it's used as a number. So that's 250 milliseconds. If you multiply these two quantities, you will find the minimum buffer. Because this router should be receiving packets from this A before this guy learns that the packets maybe they are coming or not coming from B. Is it making sense what I'm saying? That's the buffer size. We will describe it a little more into a little more details later. But this is just to give you an idea how buffer memory is sized. How do we determine the buffer memory? You see, the buffer memory relies solely on the link bandwidth, because the internet round trip is a fixed quantity. So if you have fast speed, high bandwidth link, therefore your memory must be bigger. Okay, depends on the link bandwidth. This is the link bandwidth. Okay, we'll describe it in more details later. Somewhere I'm talking about this. Somewhere must be, because that determines the size of your buffer. How you determine it. So for example, again, addressing the optimization problem, if you got a slow speed link, you really don't need to have bigger memory. it will not help you much having huge memory there. You are paying bigger memory for nothing, you're not using. Alternatively, or conversely speaking, if you have a very high speed link and you get small memory of your router will end up dropping packets. So that's a key point into the design of a router, okay? Is this clear, guys? Now, what I showed you in the previous slide is this. That's an input line card, this exactly. This would reside into a router. And that's called input interface, input line card, input port, whatever you call it. Header processing and buffering. Now, this is what is called generic router architecture, and it's referred to IQ. IQ meaning input queue. Queues are here, queue packet, and I meaning I'm queuing packets at the input side of the router. This determines the architecture of the router. Extremely important. If you don't understand this, please stop it, because this is very important discussion. Answers your question before. When I put my memory here, it means something. I could very well have moved this memory and put it here. Why not? I could. But I choose to. This is one architecture. One choice. And if I put the memory at the input side, it has applications on the performance of the router, on the speed of, on its capacity, and on its cost. We will see. These are design choices. Okay? I could very well do the header processing at the input, but yet move the buffer in there. I could potentially do it. Now, when I put the buffer or the queue at the input side, I would term the architecture input queue, IQ, input queue router. Okay? There are others, as you could understand, would be OQ, which is output queue router. That's another. And each one of them is completely different than the other and has applications on the router performance, the router cost, feasibility, and many things. Okay, we will see. That's why before, when you asked me, I said it depends. We will see that depends. Now, as before, I said you would look up your traffic, maybe you'll buffer it there, and that happens here. Now, I'm going to give you an example how it works. Okay? Now, your traffic will come there. You would understand that traffic comes in parallel, because we've got parallel interfaces. And packets coming here to this line card, they are completely oblivious of what's happening next to them. They don't see what else. All they see this link. So this packet here doesn't know that there are other packets on different links. The only question that comes in between these, the only dependence, when they come to cross this shared part. Then there will be some precedence there, and you will need some other sort of circuitry here that is called the scheduler, the arbiter, that then will arbitrate, will manage who goes first. Okay? So packets, when they come in here, based on their header, we described this in the previous slide. The header processing based on the lookup table destination address, it will tell this packet, please go here or go there or go there. Okay? The same happens to each one of them. They work in parallel and distributed and independent. Each line card works separately. Now, if you think of this, this is, and it says current generation router somewhere. Okay? This is not first generation or second generation. This is a current generation. Because first generation, second generation, they don't have this here. They have it sampled somewhere here, remember? But current generation routers, they have fully distributed processing on line cards. Okay, and this is what exists nowadays. All routers, architectures, they are like this. Now what happens, this packet here so happen to be going to outgoing interface 2. Based on its header, the lookup says, hey, I want to send you there. Okay? I don't know if you noticed that these packets happen to move there, is it? They go in there. Now, these packets, they got held here. Why? Because it so happened to be all of them, all these three packets, although they don't know about each other, they are all going to output link 2. All of them, at the same time, they want to go to output 2. However, because here, this link here, I will describe why only one of them want. Because the link speed of this is equal to the link speed of this, and therefore this one cannot absorb more than one packet at a time. Is this clear? That's why these guys, they got held there. And somebody sitting there, a guy, security guy that's called scheduler, who is overlooking the whole story. He picks who goes first, he decides. And that's a circuit that's called the scheduler that manages the crossing of packets from the inputs to the outputs. Clear? Good. Now, look at this. If I move these now, this part here, I move it here, it becomes another architecture that is called output queue. You see? The difference between this slide and the previous one is that this queue packet used to be there, right? If I move this here, it becomes output queued router. Now, this router is exactly the same as before, except there is a major difference, a big difference. That now I move the queuing at the output side. Again, it addresses what you said before. Big application here. Technically speaking, you can do this, but it has implication. What is the implication here? You can see. Now, when the traffic comes in, it would say where you go next, right? The IP lookup determines the outgoing interface. But, as you may notice now, when I determine the outgoing interface, I don't have a queuing after it, right? What happens then? What do you think? Talk, guys, talk. I'm not teaching you here, I'm discussing it. Can I repeat again? Where have you been?
Just
Been here, good. I said, previously when I do the lookup, I queue the packet in the same place, in the input side. This is called input queued switch, or route. Now, in this architecture, there is no longer queuing at the input. The queuing happens at the output. My question, therefore, when I do the lookup, what happens next after the lookup?
straight forwarding to the output.
Talk.
It's going to the output.
It's going to the output directly, because there is nowhere to queue it here. So based on its outgoing interface, it will boom, go direct there. Correct. Now, what is the implication? What's different? It goes to the output, gets queued there. So what's the difference between this queue, let's say, being here now, as opposed to that queue being here? Can you tell me some differences? Yes, please.
I think in that case scenario, the processor would be overutilized because
Overutilized.
Yes.
Which process?
let's say the scheduler in the middle, because
Yes.
at that moment it will not schedule, it will not be able to control. Packets are not being controlled. They just come.
In which case? The previous case or this case?
In this case,
It will not be able to control.
it will not be able to control because packet will just come and then they have to go straight.
But then the question, do I need scheduler at all? I don't need it. I will need scheduler only when I have people sitting there to tell who goes first. But if I have nobody, I will not need it.
Then
It's not needed at all.
So actually, that case scenario, I look at it as it basically because the intermediator, let's say like the memory, which is switching, the switching fabric
Yes.
of the switch.
Yes?
So it will be overutilized because basically like there is no this
Overutilized. What do you mean by overutilized?
packet, it is like
I will get a strong one.
it
That
is-
can handle.
There will be overflow, packet overflow into the output.
Why
which-
overflow?
It's because there is no any other measure to control actually from this other side. In case that there is efficient what you call output process for
You mean here?
packets which are
You
needed.
mean here? If I get traffic coming here,
Yes.
it will go, for example, this input, which is this same example, let's say. In this same example, I got 3 packets going to output 2, right? What happened? Only one of them went. 2 got blocked. Why? Because they are queued in this memory and there is no buffering. So I cannot send 3 packets on a line. It's a line. They will get collide. There will be a collision and data will be corrupt. So I'll have to arbitrate who goes first. Clear? Now, in this case, I move the memory from here to there. So what could happen potentially, if this same case, this same scenario is happening, all the 3 packets would be queued there. What's wrong? There's nothing wrong with it. The only implication, my friend, is the following, that this queue, continue. tell you. This queue,
It's less. It is like it's shorter than the
it's not a question of shorter. Here we are talking about
is
access
actually-
time. We are talking about the performance of that queue. This queue must be able to read in packets much faster than the previous one, which means the bandwidth of that queue must be 3 times as stronger as one here. It's required to be. Because the buffer here, or the memory, one of the key performance of a memory or its cost is what is its read and write bandwidth, access bandwidth. How many or how fast can it read data in or write it out? Okay, that's a key factor of memories. Okay, now when the memory is residing here and packets are coming here, let's say at the rate of 1 packet per second, for example, very simple case. The read-write bandwidth of this would be 1 packet per second, right? However, if the memory is here, this memory, in order to sustain the traffic, it must have a bandwidth of 3 packets per second, which means the read-write is 1/3 per second. 3rd second, it must do an operation. That's a key requirement of the memory. Otherwise, this architecture will be unfeasible. Is it clear? Very important. And that's how it works. You see, boom, 3 of them go there. Which means this memory must be able to absorb the traffic at the line speed. If, as I said before, they have a certain line speed, this memory should be able to absorb them at that same line speed, which means it must have a bandwidth of the summation of the link rates. I must tell you that the link rate here at the external line is equal at the external line here because it's input output. So if the packets they come here at the rate of 1 packet per second, they will be going out at 1 packet per second. But internally, because I don't have buffering, this must run at 3 packets per second. Is this clear? Extremely important. Same thing holds for this part here. Because this interconnect, physically, it will have some connection there. And that connection is a bus. And that bus must run again 3 times as much in order to carry the data there. Is it clear? Very important. If it's not clear, please stop me and ask me, and I'll try to explain. Okay, this is a key difference between these 2 architectures, and it's extremely important. Now, can I ask a question now? Which architecture is better than the other? Which one would you choose in terms of performance? Which would give you better performance? This one or this one? Sorry?
There is a priority for scheduling, but the second one there isn't. Because here I thought there is a drop of packets, but as you mentioned, because of the size or the capacity will be 3 times, there isn't these dropping.
No.
Yeah,
So-
but what's the priority of the packets to be cross the queue will be served
You
then?
mean here?
Yeah.
Any type of priority
We don't
of discipline you can implement here. It could be first in, first out. Push in, first out.
So it will be after that.
Yes.
But there it will be first with the shared line.
Sure. You mean this one?
Yeah.
You mean this one? This one is first in, first out in the input, but you could even implement any sort of discipline there. But the question here, it will not make sense implementing it here, because when it crosses the line, it's constrained with these different ones. It's fighting with others to cross it. So it does not make much sense to implement any priority discipline. But the question, if you talk about it, it has to be in this architecture discipline. Then here it makes sense. So did you answer my question? So which one's better? I'm saying as far as performance is concerned, assuming I'm some guy coming from another planet that they have billions of trillions of dollars. I don't care how much it costs. My driver is the performance.
The capacity, the second.
Second one.
I have one thing. Basically, let's say look at the scenario. Maybe like the link speed is very low.
You mean this one?
No, yes, basically, yeah.
Yeah.
The link speed is very low, and in that case, And on the other side, let's say like on the next op, I will find that basically there is a lot of queuing. So in this output actually in OQA, you'll find that there will be a lot of packets which will be dropped.
You mean here?
Yes.
If the link speed is slow or high?
It's very slow.
Why will it be that slow?
Because I'm just looking at the scenario. If the
Scenario, if the link
link
speed is low and this has a high bandwidth, it means that it's going to be sending the packets. This sends packet faster than this absorbs. And if the link here is slow and here is slow, okay, as long as the link here equals to the link here, it does not matter. It doesn't matter. Because here, okay, let's assume a slow link is 1 packet per second, or 1 packet per day, to make it simple. Is that slow enough?
No, what I mean in terms of the number of packets which are actually getting, there is a huge number of packets which are arriving than the capacity that.
Then the output link can absorb it.
Yes, then the output link can absorb it. So in that case scenario, what will happen? Because in this,
just let me clarify. If you get situations whereby the number of packets coming is more than what you can handle, it's an unsustainable system anyway. It's an unstable system. So here you are trying to give a scenario where it's unsustainable anyway. But what people talk about, they talk about steady state. Steady state, which means in the long run, whatever you get in should be equal to whatever gets out. Otherwise, no system will handle it, no matter what. If you see what I'm saying?
so actually, like I see actually this architecture is not really fair, because it should be able to cooperate actually in certain case scenarios.
Cooperate.
Yes.
What do you mean by cooperate?
Incorporating, like let's say like in case, because we talk in terms of where there is all the resources are available, the link speed is super fast, okay, and than the other one. What about like in that case scenario whereby you have a very good system and the your link is not really what you make? Like back in Africa, there you find that we have good system, like current system, but you find that our capacity, let's say like the link capacity is very slow and than the other one. So you'll find that sometimes, and we tend to overload for this architecture. So we try to use, we try to send a lot of traffic. So you'll find that here actually this router will get overworked, despite the fact that it is a very good system, not just because of it is not okay, its architecture is wrong, but it's because of the link. So definitely, I think in this
now
case,
when you talk about the link and the nodes, because a network is links and nodes, right? Now when you talk about mismatch between link speed and node speed, then this is the dimensioning the architecture of your whole network. It will not make sense having a super fast node and a weak link. It does not make sense. It does not make sense. It's like you are designing all the cars are Porsche that they go 300 million kilometers per hour, and everywhere in the streets it says 30 miles per hour. Why would you design a car that goes fast for a link that is not fast? You may design a car that goes 300 kilometers per hour. It costs 300 million euros, whatever you call it. But then it's unuseful, so it's waste of resource. So the example you are giving me are saying the links are weak, but the node is fast. Is that what you said?
yeah.
This is a different discussion. This is about dimensioning your network. But here, my feeling is when I ask a question, guys, you answer me about something else. My question, solely speaking, given that the same links are there, which architecture is better, this one or the previous one? The answer is this is better. Much better, in fact. Because this would absorb all the traffic here. Because the problem is in this shared resource. Once you get traffic crossed to its outgoing link, then you are pretty much done. The problem happens here. Because in this architecture, what's happening? All the traffic is fighting to cross this shared link. Once you get it across the river, then you're safe. You can do lots of stuff. Okay, and in order to do that, you will have to have this is running fast enough, and you should have memories that are able to cater to absorb. That is expensive. It is expensive because it means that you should have much faster interconnect and much faster memories. But provided that you have lots of money, you can afford it, then it's good. Okay. What else I'm going to cover? We are running a little bit out of time now. But I must say, comparing input queuing to output queuing is much better. However, the most practical is input queuing because it's affordable price-wise. Output queuing is very expensive. Sometimes output queuing is not even only very expensive, it's simply unfeasible. There is no such technology nowadays that allows you to build a super fast output queued router. For example, a router that has 256 by 256. There's 256 interfaces, and each interface is running 40 gigabits per second. You may do your math, you will find that there is no such memory on Earth that is as fast as absorbing 240 packets, each one of them running 40 gigabits per second, and each one of them is of size 40 bytes. There is no such memory that does this. Simply, technology does not allow. Okay? So what I'm saying, output queuing is a good architecture, but sometimes it's unfeasible, let alone very expensive. That's why people usually, 90% of the architecture that they exist on the market, they are input queued. The buffering happens at the input. And when the buffer happens at the input, the memory does not need to be running very fast. It runs only at the right speed. We'll see details of that. What you are seeing now is an example of a real line card that is input queued line card. Input queued, the traffic comes here. You can see the direction of the traffic. This is input output at the same line card, so this is a real one. And you can see that buffer management and scheduling happens at the input side. Is here. It's not an output. Over here, an output. So this is a typical one. Okay. This is the backplane, the crossbar, and this is scheduler, the crossbar here. Okay. Now this is OC192, which is 10 gigabit per second line card. This is a typical one. This line card here contains lots of functions from the data path, as I explained before. So it could hold anywhere between 10 to 30 million gates, which means the circuit design there. It's in the order of 2 gigabits of memory. 2 gigabits, it comes from the 10 gigabit per second line card multiplied by the internet round trip, you would find it maybe 2.5 gigabits. Here we say 2 gigabits. It's okay, 2 gigabits are fine. It takes in the order of 2 square feet, and it costs anywhere between 10K to 100K US dollar. So imagine if you got a router that has, what do you call it? That has a number of these, let's say 32, which is typical number. You could do the math to find out the cost of your router. This contributes a lot to the cost of the router, the interface. Okay? They are extremely expensive, so they are in the order of millions. These ones, we have 32 by 32 at 40 gig plus. Okay? What else I'm going to talk about? We still have quite a bit to cover today, but we are going to be running out of time. It's all right. Now, performance and limitations. So the main key performance point of a router is its capacity. Capacity is the number of bits per second the router can handle. Okay? So, which is referred to as C. So normally it's a maximization or optimization problem, whereby we say we would love to maximize C, the capacity, subject to. I would like the router to be not taking much space, so I don't need to have too many line cards. And I would like the power to be up to a certain budget. Power is very important here. Okay? So usually speaking, that's how people would think about it. The C is the capacity, which is throughput. Okay? So operators, normally they would like to maximize the usage of their expensive long-haul links, so which means they would like to have high throughput router. And they also would like to have controllable delay. What it means? It means operators, they would like to have their customers being served on time. They have controllable delay there. So the traffic does not get delayed. And if it does not get delayed, it goes without saying that you serve more customers and customers are more satisfied. Okay? So some users, maybe even they would like predictable delay. So there are some, for example, companies, for example, banking companies, okay, the stock exchange companies. they fight over, I don't know, a millisecond delay, or even less. Okay? So they require some sort of predictable delays. In order to achieve this, usually, the architecture of choice to control your delay is to implement an output queuing switch, the one I showed you before. That one would provide you some controllable delay if you implement it with some sort of what they call weighted fair queue. We will see this in the quality of service guarantees in the last 2 lectures. Okay, but just to give you an idea. What else? Why do we need them to be fast, the routers? Why do we need fast routers? Good question. Because we would like them to be not the bottleneck in the internet. If routers are fast, they absorb traffic, therefore the overall architecture or the overall network or the internet as a whole will be delivering good service, so they will not be the bottleneck there. Because in simple terms, the internet or any network is a combination of links and nodes, and the nodes are the routers. So now the links, nowadays they are extremely mature transmission links. With the optical transmission lines, you can have lots of data transmitted cheaply and very reliably. So what is the problem therefore? The burden has moved to routers. So that's why we would like to have routers fast. So link technology is climbing fast. Users are growing a lot in the world. There are many users now with computers. So networks are expanding at the edges. Links are fast. What is that? Routers. Routers, they need to be faster. That's why we would like to need them to be fast. And also, we need them to be fast, generally to increase point of presence capacity. POP. POP is the big offices where we call them point of presence for big networks. Okay? And reduce cost, size, and power. And POP, I showed you that in the first lecture, I guess, on the architecture of the backbone networks, where they have what is called network exchange points, and the point of presence, central offices, and how you exchange data. We covered that 2 weeks ago. Okay. Now, this data is dating back a couple of years ago, but the trend is still the same. Why do we need the routers to be fast to prevent them from being bottleneck? This is giving you the normalized growth since 1990 for actually 20 years. You want to say something?
No.
Oh, good. Now, all these lines, what it says, the first one here, it says line capacity, transmission links. Transmission links actually are doubling roughly every 6 months. So we get 4 times the speed pretty much every year. Clear? The next one is user traffic. User traffic from 1990 all the way to 2000, I think, 5 is that? Somewhere there. It's doubling actually even more than twice per year. And this is because of, the proliferation of reachability. Many people now, they are connected to the internet, the diversification of applications and all of that. I'm not going to be mentioning what is making the user traffic getting high. User traffic is getting a lot with videos now online, YouTube, I don't know, Facebook, Twitter, everything. So user traffic is really very climbing a lot, okay? Now, what is left, this line here, is router capacity. Router capacity is doubling roughly 2.2 every 18 months. So it's not keeping up with the links and the user traffic, okay? What else is there? This one actually is Moore's law, which is similar to this one, as you can see. Moore's law, there is a scientific of Bell Labs in 1964, he said, the law of Moore. You know Moore's law.
Doubling every 2 years,
Yes.
something like that. But here it mentioned 18. But it's based on doubling.
No, it is 18 months, not 2 years. Okay?
Yeah, some
And
sort.
it kept on. Okay? So router capacity is trying to keep up with that. But we see there is lots of stress on that. Okay? Now a very funny thing. As you can see, the very low one here. Memory. Random access times of memories. DRAM, random access time. It really was suffering all the time. Memory problem. Memories are not keeping up. unfortunately, memory contributes a lot into the router. And the data path of a router contains lots of buffering and memory. And this is what is preventing routers from keeping up the pace. Okay? This is just to give you an idea what are the challenges into making routers growing faster. So the big work in routers is how you place memory, how you arbitrate, how you try to come up with smarter and faster algorithms, for example, for lookup, for buffering packets and all of that. Okay, buffer management, basically. And also, of course, memory technology itself. All right? Now, what else? This here, it's just trying to, to explain why do we need faster routers and bigger routers. So if we have faster routers or bigger ones, we would reduce the cost, power, and complexity of point of presence. This is an example of a point of presence, okay? Now, big POPs need big routers. Now, imagine these two scenarios. It's the same point of presence, the same network, let's say, the same operator, but they got two choices. Either to have, how many routers? 3, 6, 8 routers in this topology, or 4 big routers in this topology. Which is better, you think? These ones. Why? Because now you would use the routers in a better way. Because as you can see here, most of the traffic here, or the bandwidth, is consumed internally for reachability. Why? Because they don't have many interfaces, they're small. But if you get a big router, therefore you could achieve better. You could get a better user traffic, okay? And of course, the interfaces here are very expensive, as I said before. In this case, as you can see here, about 50 to 60% of the interfaces are used for interconnection within a POP when you have small routers. So half, if you can think, you can calculate the number of useful interfaces to the total number. You'll find most of these interfaces are not used then. They are used to interconnect them. Okay? So roughly half the capacity of your routers is used internally, okay, for reachability. If you get it big here, as you can see, you will see that you are using the routers, the interfaces in a better way. So that's why we need them to be faster and bigger, actually. Okay? And the trend of the industry is usually to have a big point of presence with ideally big router, actually. Okay, single router to POP. Now, again, why do we need them to be faster? This is user traffic. You say, user traffic prediction of this year, the user traffic is 5 times more than router capacity. What you mentioned before. Okay? So that's really a big disparity. 5-fold, you say? So that's why routers are needed really to keep up the pace. And that's the goal of what we are studying in this module. We are trying to understand, for some of you who are interested in this area, maybe it's a good topic to focus on, even for your work, whether a history of research, because there is lots of work there. Especially nowadays, there is what is called the cloud computing and data center networks. And they rely a lot on routers. Okay? This is telling you now, we need them to be fast. But why can't we have them fast? They are hard to make them fast. Why? Because, again, memory access speed. Memory is the problem. So this is a big disparity, as it says, between line rates. These are the line rates, but that's the memory speed. So the line rates, the traffics, the line capacity keeps to declining very fast, but memory access speeds are not improving. And that's the technology. Technology does not allow you to go very fast. Okay. For example, here I'm giving you an example. Assume that I have a line, and this line, by the way, it's no problem. The capacity of lines is going very fast. I could push lots of data, high bandwidth in lines. It's bothering you, the light there? Good. So this line could afford to have lots of bandwidth, high bandwidth there. However, my memory is a problem. Okay? What it says assume that I have a 40 gigabit per second buffer. This one can handle 40 gigabits per second. It can handle up to 40 gigabits per second. Okay? That's the bandwidth of the buffer. Now, in order to cater for my buffer here, in order to size it, I gave you the example before. In order for TCP to work well, the size of this must be the round trip times its bandwidth. Okay? And that would give you roughly 10 gigabits. That buffer needs to be, roughly speaking, 10 gigabits in order for the router to be sized properly. Here, if I assume 64-byte packets coming, so assume that the chunks that they come here, they are units of 64 bytes, which means the operations, every atomic operation is done on a piece of data that is 64 bytes. Okay? Now, assume that this is 40 gigabit per second line. Okay? And I got 64 bytes packets. Every entity is 64 bytes. Therefore, you will need to write a packet here, roughly speaking, every 12.8 nanoseconds. Do you know how you find out that? No. The write rate, or the access rate, is the packet size over the link speed, over the bandwidth. Packet size 64 bytes. I'm getting packets here, each one of them is size 64. And this absorbs 40 gigabit per second. So roughly speaking, after how long will I have another packet coming? It's the line rate divided by the, or the packet size divided by the line rate. So if you divide 64 bytes by 40 gigabit per second, you will find that. It's how many people you can get.
The start of sending the packet.
How long will you need to treat each packet to process it? So this is bytes. So in order to make it, and this is bits, so that's why you do the conversion, you multiply by 8 there. So you will find, roughly speaking, 512 divided by 40 to 10 to the 9, you will find that number. Which means this buffer here, we need to write a packet every 12.8 nanoseconds at this, with these specifications. If I have this line rate, which is typical line rate nowadays on the internet, and this is a typical IP packet size. With these specs, you will need this buffer to be able to absorb packets, to write them in when a packet comes in. Remember that before we said you need to do the buffering, the queuing? Buffering meaning writing the packet into memory. You will need to have that memory running as fast as 12.8 nanoseconds to do an operation, a write operation. Okay? Mind you, and this buffer also, at the time it's writing a packet, it must also read another packet out in order for efficient use. And the read operation will also cost you 12.8 nanoseconds. Okay? Now the question is, I got this buffer size, 10 gigabits, and I got a constraint that that 10 gigabits should have a read and write access constraints of 12.8. The question now, what type of technology would give me this? This is basically the question. I'm trying to design around it. And memory technology, there are a number of them there, with each with pros and cons, and costs also. So there are two questions. Do I design this to be an SRAM, static random access memory? Please go and read what a static random access memory means. Do it on your own time. I got you some readings, okay? An SRAM is fast enough random access time. It's very fast random access time. However, it's too low density to store 10 gigabit of data. SRAMs usually they are used for on-chip memories, for caches. On your computer, when you say, I got a cache, that's an SRAM. But an SRAM is quite not dense, because you will need big space to store 1 bit on SRAM. You need a refresh bandwidth or a refresh cycle very high, so that's why you will need, roughly speaking, 6 transistors for 1 bit. That's why you will need lots of space per bit. And that's why it's too low dense for this much data, 10 gigabits. Okay, so SRAM maybe is not a good choice, because we don't have an SRAM that holds 10 gigabits. SRAMs, they hold in the order of megabytes, not gigabytes. Biggest SRAM. The other end of the spectrum is DRAM, dynamic random access memory. It has a very high density, but the problem with the DRAM it's not fast enough. DRAM are slow. So you see now the trade-off? That's the DRAM there. Do I use DRAM? Yeah, it says it's very good, it does. It can store lots of data. DRAM, you can have gigabytes. But the problem with DRAM, the access time is very slow. The fastest one is in the order of 50 nanoseconds. Did you now understand the challenge? That's the problem. I'm going to stop in 2 minutes. These are some costs. Memory technology and trends, and it gives you the technology type, TCAM, networking DRAM, or SRAM. What can you have in a single chip of this type, okay? So you can go in a single chip, 128 gigabytes or 16. And this is the price per chip per megabyte. This is the access speed, very important access speed. You can see that the TCAM is the fastest, SRAM next, and then networking DRAM is there. It also gives you the consumption, power consumption, which is again extremely important. So, to recap, I'm going to stop here. Unfortunately, I will continue next week because we still got a number of some content to cover today, which we are not going to be able to. What else? We'll talk about this later. The takeaway message of today is to appreciate and understand the architecture of our. How did they have their historical evolution over time, different generations? The data path, very important, and we reached the story of memory, which is the big key question into improving the large terminals. Okay, and next week we'll continue the rest. I'm going to stop here, and if you have questions, please don't hesitate to come. Okay, bye.
不把那个大尾巴连闭着。我天。